Good morning, everybody. Let me get this going. Alrighty, we are ready to go. Welcome to OChem. This will be everybody's favorite subject, I'm sure. And you're not going to hate it at all, and it'll be very easy, and everyone will get A's, right? So, no, I'm sorry. Unfortunately, it's probably not the case, but that'll be okay. So, hopefully, everybody has had a chance to look at the syllabus and watch the welcome videos and all that. So, we should be good to get going. Good morning. Good morning. Yes, it should be fun indeed. Kevin, what are you doing here? I thought you couldn't make it. Okay. Anyways, let's get started. So, if there's nothing with the syllabus and all that fun, we'll go ahead and begin. So, organic chemistry really is the chemistry of carbon. Hello. It's so many familiar names. It's great. So, when we're dealing with carbon, we're going to see that. Hello, Alan. Dealing with carbon, we're going to see there's going to be some kind of base rules we want to set, and we're going to have a lot, and I mean a lot, of all sorts of different things that are going to happen with that carbon. Got it. Cool. Alrighty. So, a couple things to keep in mind when we're dealing with carbon. Rule number 1 in this class, okay, sounds good. Rule number 1, always. Yes, it is. It is the tiers. So for sure. Rule 1, never, ever give carbon more than 4 bonds. Actually, we can give it equal. Why did I put that? In fact, most often it has equal, right? We can see that in kind of rarer situations, we'll have 3 bonds, maybe even 2, not very likely, but 4 bonds is ideal. We can never, ever go above 4. And so let's take a few minutes here to kind of review some of our stuff from 111, where we talked about Lewis structures and that sort of thing. Let's look at a couple of basic molecules here. For example, methane. Hopefully Lewis structure was not too crazy about that. Note here we have carbon with 4 bonds. In this case, we have 4 single bonds, each of them to a hydrogen. If we take a look at, say, formaldehyde, in this case we have 4 bonds, just like before, though in this case we have 3 single bonds, 1 double bond. And let's say if we do carbon dioxide, here we have, again, 4 bonds, although both of them are double this time. So we're going to see that no matter, kind of what we're doing with this, the carbon's still going to have 4 bonds in 99.9% of all cases here. Again, we can go below 4. We'll have carbocations in that case, or maybe carbines, depending on what we're talking about that day. But by and large, 4 bonds. That's our rule here. Can never go above 4. That's kind of one of the common mistakes when we start doing resonance, either later today or next week, is people try to give carbon 5 bonds and then everything explodes and that's the end of it. So never ever give it more than 4. Just looking at these molecules here, we see that we have 4 sigma bonds in this particular molecule, the methane, right? Remember that sigma bonds are what we would call single bonds, right? Every bond is at least a little bit sigma. We could throw on pi bonds as well into our molecules if we want. So if we see in the next 2 cases, we are going to indeed have now 3 sigma bonds, Remember, those are the single bonds, and then in this case we have one pi bond as well. That's the second bond to the oxygen there. And then on our carbon dioxide, we're going to have 2 sigma bonds and 2 pi bonds. Hopefully this is vaguely familiar to you. I can even do the pi bonds in blue, because why not? Oh, I lost a sigma, and now I'm all over. Alright, we'll do these. Okay, so we can say our sigma bonds are in black, our pi bonds are in blue. Hopefully nothing too crazy here. Should again be somewhere in your memory. Anytime you have the multiple bonds, those are all pi bonds. If we want to take a look at the orbitals that are going on to make these bonds, remember that in order for carbon, if we remember carbon's electron configuration, it's 2s2 2p2, right? If we want to have 4 bonds, though, I mean, typically we'll think, okay, don't mess with the s electrons, they're already happy, you know, we already have our kind of full orbital there. Remember that for carbon to make 4 bonds, it's going to need to use 4 electrons. Remembering that s electrons are lower energy than p electrons, we might think, okay, we're just going to have 4 electrons to work with. We'll just go ahead and we'll promote one of those s electrons up to p. Now we have 4 electrons, we can make 4 bonds with them. But remember, as we talked about 2 semesters ago, we find that the bonds in methane, which has 4 sigma bonds there, are all identical to each other. So they all have the same length, which means that we probably don't have 1 s orbital and 3 p orbitals, but in fact they will have hybridized into 4 sp3 orbitals. And we'll go ahead and throw our electrons in there. Remember, this is the process of hybridization. It's a way for us to make equal energy orbitals so that all of our bonds will be equivalent in the molecule. And again, we have experimental evidence that shows us that methane all has equal bonds from the carbon to each of the hydrogens. Or if we throw away those hydrogens and put other atoms on, if we throw chlorines or oxygens or whatever, we're still going to have equivalent bonds there. So it kind of, you might think, okay, well, this hybridization stuff is kind of just our way of making this make sense. We don't really have evidence for hybridization otherwise, and that's true. It's kind of just the theory that shows us that, or a way to explain how we can make carbon have equal bonds. That being said, we can take a look at these other molecules and look at their hybridization as well. And I get we're zooming through this because hopefully this is somewhere in the back of your head again. But if not, I think these are all covered in the first chapter of our book in pretty good detail. So if you have forgotten that stuff, you may want to take a look again at those. So this tells us that these sp3 orbitals, we're going to end up with 4 sp3 orbitals by combining the s and 3 p orbitals to make them of equivalent energy. We have 4 of them, and that means we can make 4 equivalent bonds to whatever we're going to be working with there. And so, remember, carbon will only ever make 4 bonds, sometimes 3, I'll concede that again, but 4 bonds by and large most of the time. And so we're going to see here that we're going to have sp3 hybridization occurring within carbon whenever we have only sigma bonds. All of these will be sigma bonds when we're talking about sp3 hybridized carbon. So anytime we see our methane, or why not throw methanol in here, or I don't know, carbon tetrachloride, or ethane, all of these carbons are sp3 hybridized for all of these. Because we have no double bonds. That's the easy way. Easy way to think of an atom. If it has only single bonds or lone pairs, that means it's going to be sp3 hybridized. So if I were to mark on these, all these, actually the oxygen too, all these starred atoms are sp3 hybridized. Hydrogen cannot be, right? Hydrogen does not have p orbitals. It only has s orbitals, and it only has one electron. So oxygen or hydrogen is only ever going to have just s. But all of these atoms that I've starred here are sp3 hybridized. And so that's kind of the very first thing I can ask you, is to take a look at a molecule and identify hybridization of my atom of choice, or atoms of choice. And we'll do plenty of examples of those in a little bit. We're going to cover the other two hybrid states first. Just one thing to note as well. Hydrogen is never hybridized. We're going to have s orbitals only here. All right, so just remember that. So we can have hybridization happening on any other atoms besides helium, I suppose, but helium doesn't bond with stuff, so it's okay. We're not going to need to make bonds with helium. Alrighty. If we want to take a look at this methane again, and let's say I want to look at this bond here in particular. If I were interested in talking about what bonds are involved, or what orbitals are involved in this bond, and in fact, let's just do it on the ethane instead, because why not? It's closer. If I were to look at this bond here, we know that that carbon is sp3 hybridized. Again, how we tell is because there are no double bonds on it. Single bonds only means sp3. So, given that that carbon is sp3 hybridized, we're going to have an sp3 orbital. I should make that higher. There we go. This is our carbon here. And remembering, hydrogen must always be s. S orbitals, if you remember, are spherical. That overlap there is what creates our single bond here. And so that's going to be our sigma bond. So we're going to see we have the 2 sp3 orbital and a 1s orbital from hydrogen that are taking place to make this bond. So we have the sp3 overlapping with the s orbital, holding those together. They're sharing their electrons. That's how we're going to make our covalent bond. So we're going to see that the orbitals involved there for this particular bond are, for carbon, we have a 2 sp3 orbital, 2 being that it's in that period 2, and then we have the 1s orbital of hydrogen involved there, overlapping to make that single bond. If we were to look at, oh my goodness, I'm running out of colors here. If we were to look at this bond, the carbon-carbon bond, we're going to see the orbitals there will be two different sp3 orbitals. Exactly, yeah. So we have a two sp3 from one carbon to two sp3 of another. And so remember, sp3 orbitals kind of have this little lopsided dumbbell shape, so they have a big side and then the small little side there. We often just ignore those small little bits at the end there, but that overlap there is going to give us our carbon-carbon bond. And so we're going to have a single bond happening there as well. All right. Cool. If we were now to start throwing in double bonds, we can take a look at a few molecules like that. Let's look at sp2 hybrids. That means that we're going to have 3 sigma 1 pi for anything that's an sp2 hybrid. Some examples. We saw that the formaldehyde earlier had sp2 hybridization on the carbon and on the oxygen. We can see that something like ethene will have sp2 hybridized carbons. We can have, I don't know, thionyl chloride here. No, thionyl chloride has the oxygen. Regardless, I'm going to just ignore lone pairs for right now. They're not really important because we're not looking at the chlorines really, or the sulfur, or the oxygen. Focusing on the carbon here, all these have sp2 hybridized carbon. We also have what's going to be one of your favorite molecules, at least next semester, benzene here. Or if we were to, goodness, okay, hold on. I hate drawing things this way, but we haven't learned the other way yet. Okay. All of these carbons in benzene are sp2 hybridized. So we got plenty of sp2 here, sp2 hybridized carbons here, and a few other atoms that are also sp2 hybridized. If we want to look at what's happening there, if they have 3 sigma bonds, that means they're going to only need to hybridize. Let me give myself a little more room here. If we only need 3 sigma bonds, we only need to hybridize some of them. We're going to leave one of our p's out, because p orbitals do not make sigma bonds. So we're going to see that we're going to have that extra p orbital that's going to make our pi bond later on. And so we only need to fuse kind of that s orbital with 2 of the p orbitals. And now we have 3 sp2 orbitals of equal energy and 1 higher energy p orbital. So remember that p orbitals will always have higher energy than any hybrid orbital, whatever that hybrid happens to be, sp3, sp2, sp1. And then s orbitals will have even lower energy. But if things are to be equivalent, if we need 3 equivalent single bonds, which again evidence shows us that in these molecules we do, we're going to need to hybridize them. And so we're going to have 1 extra p orbital here that's going to be able to participate in some fun stuff as we go on. So let's take a look at some of these. Let's look at this the ethene molecule here. Let's look at that one. I'll just redraw it actually. So we see we have again on each carbon 3 single bonds and then in between the two carbons a double bond. If we want to take a look at what those orbitals are, we're going to see that if we kind of just draw the sp2 orbitals of the carbon, oh goodness, let's see if I can do this. Again, I'm kind of ignoring those little bits of the sp hybrids. If we put on our hydrogens here, we have this happiness happening. These are all of our hydrogens here. That's the carbon, that's the carbon. But now we also have p orbitals. And let's do those in green. P orbitals are equivalently big on either side. sp orbitals, or spx, whatever hybrid, they have kind of a, remember they look kind of like that. They've got this little itsy bit on the other side. P orbitals are just the same up and down. So this is a p. This is some hybrid orbital here. When we have p orbitals, those kind of overlap a little bit. Not like the sigma bonds where we actually have orbitals directly overlapping with each other. With pi bonds and p orbitals, they can kind of just tilt towards each other and kind of like make a bridge in between them. So the amount of contact is not the same as a sigma bond, right? A sigma bond, you have actual overlap. Pi bond, you kind of have this they're close together idea, and they can kind of share in between that space, but they're not directly overlapping. And so this green thing here is going to be our pi bond. And all those other, I guess in this case black, those were all sigma bonds that are in between all those molecules. Couple things to remember, because there's less overlap between a pi bond and a sigma bond, pi bonds are always going to be weaker, right? So pi bonds are always weaker than an equivalent sigma bond. Reason for that? First off, p orbitals are higher energy than spx, whatever those happen to be. And second of all, the amount of overlap between two p orbitals is less than the overlap you'd have in a hybrid orbital interacting. All right, so pi bonds are always going to be weaker. We're going to see when we get to chapter 7, when we start talking about alkenes, we're going to be breaking those pi bonds fairly easily, doing things that will not be able to break sigma bonds. And so we're going to have plenty of reactions when we talk about those, because these pi bonds are weaker in energy. I'm sorry, they're weaker in strength, they're higher in energy. So, fun stuff. Alrighty, so taking a look again just at orbitals, just getting this in there, setting the foundations for all the fun stuff we're going to do here. Alrighty, let's look at SPs. These are going to be molecules with 2 sigma and 2 pi bonds. Classic example here is acetylene or ethine. Some people, well, ethine I think is the preferred name, but acetylene is probably more common. Just like ethene is the name of the one before, but most people call it ethylene. So that's what people do, I guess. We can also have 2 double bonds instead of a triple bond, but either case it's the same. We're going to see that nitrogen is much the same as this. Remember that lone pairs, these lone pairs on nitrogens, kind of count as a sigma bond. Lone pairs are kind of going to be located within hybrid orbitals always, so we'll just throw that in at the end there. But let's take a look, because mostly we're focusing on carbon. We don't see carbon with lone pairs very often because it's not very stable. We'll talk about those. Those are called anions. Sometimes we'll have carbines as well. That'll have carbon with lone pairs, but those are very, very reactive. So, looking at these, with this particular carbon here, let's look at this carbon. It's got 2 sigma bonds. It's got 1 sigma bond to the hydrogen, 1 sigma bond to the other carbon, and then it also has 2 pi bonds in between the 2 carbons there. So if we're looking at that one, we're going to see that it's going to have, I guess I've been doing these in black, so let me do my SPs in black there. That's our first SP. That's our second one. It looks like a p orbital just because I'm not drawing the little taily bits on, and it has the same kind of linear geometry that a p orbital would have. It's that 180 degrees. But here's our hydrogen. Here is our other hydrogen. We have our sigma bonds there. And so now we're going to have a p orbital up. That's going to be overlapping a little bit, up and down. And then here comes the fun part. Let's see if we can do this in 3D. We have a second p orbital going in and out. That's going to overlap again. I apologize, my 3D drawings are always terrible, but you all know that by now. So, fun. So we're going to have now one set of p orbitals overlapping vertically, one set of p orbitals overlapping horizontally, and that's going to give us our triple bond there. If we take a look at the carbon dioxide, let's go ahead and do that. So we've got our sp orbitals. We've got some sp2 orbitals from the oxygen. We've got our carbon in the middle. We've got our oxygens here. In this case, we're going to have one of carbon's up and down p orbitals, the pz orbital, let's say, interacting with the pz orbital of oxygen. And we're going to have our horizontal one, maybe that's px, interacting with px of the oxygen there. Again, it's hard to tell, but pretend those are 90 degrees apart. Again, I'm terrible at drawing, but we already know that as well. So there we have it. So that's another way to kind of figure out visually what those pi bonds are looking like. If we look at the hybridization, since we only have 2 sigma bonds per carbon, we're going from our original configuration, hybridizing to have 2 sp orbitals and 2 p orbitals. And so we're going to have 2 sigma bonds and 2 pi bonds as a result of this. And how exciting, we're going to end up having our sp carbon after that. All right, so anytime you see 2 double bonds on a particular atom, either that's a triple bond or 2 separate double bonds, that's going to indicate sp hybridization. All right, so what's the point of all this? Well, we have a couple of things to say here. Remember a few things. If we want to think about the bond angles here, remember that sp3 hybrids, we're going to make 4 bonds. 4 bonds means 4 electron domains. 4 domains means tetrahedral. And that means you're going to have those lovely 109.5 degree bond angles when you're dealing with something that's sp3. If we're dealing with anything that's sp2, those are going to be trigonal planar. Those are going to have 120 degree bond angles. And anything that's sp is going to be linear. And that'll be our 180 degree bond angles. So just taking a look here. We've got our examples of each different type here. So the carbons in these molecules follow those hybridizations. And those bond angles are going to be present as well. So the bond angles here, 109.5, 120, 180. So we're going to say the geometry is going to be, it'll be changing depending on what our hybridization is. And we're going to see again later on that's going to affect reactivity of things as we go. And we're going to see, because we have the sp2 and sp hybrids that are planar, we can have things attacking from both sides. We're going to have all sorts of fun when we talk about stereochemistry in Chapter 5. But we'll get there. So those are all of our different kind of hybrids there. Easiest way to tell, just look at the number of pi bonds you have. That's going to tell you the hybridization of your atom of interest. All right, so let's take a look at a couple of examples. Let's say we have okay, here's a fun little molecule here. If I were to just give this to us and say, question 1 here, how many sp3 hybridized atoms do we have here? If we want to think of that, we're looking at anything that's not a hydrogen that has no pi bonds. So that's what that question is asking. So something that's not a hydrogen and no pi bonds. All right, so Kevin says 2. Let's see if he's right. If we just go from left to right on this, we're going to see that we have hydrogen, so skip it. We have carbon with a double bond. We have oxygen with a double bond. We have carbon with 4 single bonds, so that'll qualify. Oh, now Kevin has told us how many sp3 carbons, but don't forget lone pairs on these chlorines is also going to make those sp3. So no pi bonds on those chlorines is going to still have them be sp3. All right, and indeed we're going to have that other carbon there that has the single bonds is going to be sp3 hybridized. So don't forget kind of like outer atoms that we might be not thinking about. So our answer here is going to be 4. So we're going to have 4 sp3 hybridized atoms in this molecule. All right. Same thing with sp2. So for this one, let's do it in blue. Again, ignore hydrogens. Hydrogens are only s orbitals. We're looking for things that are not hydrogen. Oops, that should be not. And that have 1 pi bond. Yes. So Kevin's already got it. So if we're looking, again, skip the hydrogen, we see this carbon here that's next to that. Indeed has 1 pi bond on it. The oxygen it's bound to also has 1 pi bond. The only other non-hydrogen atoms we have here are those triple bonded carbons. Triple bond means 2 pi bonds, so those are not going to be sp2. We're going to therefore have just the 2 of those. Yes. And then if we're looking at sp, as we've already kind of now just said, we're going to have those 2 be our sp hybridized carbons. So we're going to have 2 of those as well. All right, so again, no hydrogens, and we're looking at 2 pi bonds. And so that'll be those 2 carbons there. So we're going to see that we're going to want to get familiar with being able to identify hybridization on any particular atom in a given molecule. Remember, hydrogens never hybridize, they're only s orbitals. But any other atom starting in period 2 can have hybrid orbitals, and probably will if it's in a carbon-based molecule like this. All right. Any questions on that one? Alrighty. Then let's talk about kind of drawing organic molecules. Because we're going to see pretty quickly here, I will never give you a structure like this again. Because it's a pain to draw. We typically don't draw molecules, Lewis structures like this in organic chemistry because it just takes too much time. And plus, we're going to see that since most bonds are going to be carbon to hydrogen, just drawing those in every single time gets a little bit tedious and messy. So we're going to see that if we draw something like this molecule, butane, we're going to see pain in the ass to draw this. We have other ways of doing it. We can kind of condense this and just say, okay, we've got something like this. This is a condensed structure. This is a kind of a Lewis structure here. We can condense that down by just saying, okay, we have CH3, CH2, CH2, CH3. And hopefully you can see how we've gotten that. We see we have CH3 right here. We have CH2. Another CH2. And then a CH3. And so that's how we've condensed this. Because carbon or organic molecules very often include long chains of carbons, that's how we kind of imply this condensed structure. We list the carbon first and then whatever's on that carbon after it. And we just keep going along our carbon chain from left to right as we go through this molecule. We're going to see, however, that doing these condensed structures is still somewhat of a pain. And so really, we're going to end up most often just drawing this molecule like this. And what the heck? This is called a skeletal structure or line angle. And this is identical to the two structures above. They're just different ways of showing kind of the same molecule here. But look at how quick it was to draw that skeletal structure than it was to draw everything else. How skeletal structures work is each vertex is a carbon. So instead of writing out C, 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 C everywhere, we just leave it as a vertex. So we have 1, 2, 3, 4 vertices here. All of those are carbon. If we look at our Lewis structure, indeed we had our 4 carbons there. And then the other key component to the line angle structure or the skeletal structure is that hydrogens are not drawn in explicitly. We don't draw in the hydrogens because we are going to assume has 4 bonds and that any undrawn bonds are carbon to hydrogen. So a skill that's going to be very important for us is being able to just take a look at a structure and being able to say how many hydrogens are on a particular carbon. So we have to keep in mind that a carbon is going to have 4 bonds unless indicated otherwise. Again, 99% of the time we're looking at 4 bonds. And so instead of drawing out all of the bonds, we draw anything from carbon to non-hydrogen, whatever other atom that is. If it's carbon, oxygen, sulfur, whatever, we'll draw in everything that's not hydrogen. And we're going to assume that everything else that's not drawn is hydrogen. So if we were to take a look at this, we would say, okay, this carbon here, that leftmost one, has 1 bond to the carbon next to it. It has to have 4 bonds total. So because there's only 1 bond drawn there, that carbon needs to have 3 more bonds, and so we'll have 3 hydrogens stuck onto that carbon. And so if you really wanted, we could say, okay, yes, here they are. Here are those 3 hydrogens to make sure that our carbon is happy. And if we were to then look at the next carbon, we'll say, okay, that one has 2 explicit bonds drawn, which means for it to have 4, there are 2 hydrogens that are not drawn there. That is true, but we'll talk about alkanes later on. So right now we're just doing kind of foundational stuff. So if we're looking at total number of hydrogens, that is correct. We have 2 times the number of carbons plus 2. But I would like to focus right now on just looking at individual atoms and looking at how many those might have. Let's take a look at a couple of examples. Here's a molecule. If we want to draw this as a Lewis structure, we can do that. Let's first identify how many carbons are in this. Well, for this, we're looking at how many vertices, right? So we're going to see we have, oops, 1, 2, 3, 4. And indeed, yes, we're going to have 4 carbons in this particular molecule. Every vertex there, which I've now put a little dot on so you can see them. So if we're going to draw this as a Lewis structure, we can start by putting our chain of 4 carbons on. Let's go ahead and put in all the other explicit atoms here. It looks like on that second carbon we have a double bonded oxygen, so we could put that down. And it looks like on that third carbon we have a chlorine. And that's the last of the explicit atoms. And so if we then want to complete this, we're going to have to include all of the hydrogens on this. So we can. Every carbon needs 4 bonds. So we're going to need to put in as many hydrogens are necessary so that we have 4 bonds in there altogether. All right, and so that's kind of our Lewis structure that we're looking at here. So again, we've omitted all the hydrogens on our skeletal structure. Every other atom we do put on, only hydrogen can be kind of hidden away. But again, since we see here there were 7 hydrogens in this particular molecule, it's going to save us a lot of time if we don't have to draw 7 hydrogens, especially when we get to molecules with 20 carbons. Can you imagine how many hydrogens that are going to be there that are just going to make things messy? It's a way of being very clear, and it's kind of the standard across the board for hydrogens to be omitted in organic chemistry. So keep that in mind. Let's do some more. Here, I'll keep that there. All right, let's take a look at this molecule. So notice, by the way, that we can get rid of hydrogens that are on carbon. We can hide those away. But hydrogens on what are called heteroatoms, anything not carbon, must be written in. So just one kind of little note there. Heteroatoms again means not carbon. Since OChem we focus on carbon, we call anything else a different atom. These must be drawn. Oops. Yeah, that's good enough. Drawn on a skeletal structure. So when we talk about molecules like this, we are going to include hydrogens that are on heteroatoms. Heteroatoms typically, again, are going to need to make their octets as we go back to Lewis structure. And so just to make things very clear, we are going to always indicate our hydrogens that are on heteroatoms to make them have their octets. All right, so let's take a look at this as a Lewis structure. Let's go ahead and dot our carbons. I'll use blue again for this. We're looking at every vertex in this molecule. So we have one here, one here. So all together, we have 7 carbons in this, 6 of them as part of a ring, and we have kind of just one sticking out at the side. if we were to draw this as a Lewis structure, okay, I can do this. This is kind of the base of it all. Note, we do have a double bond to a carbon-carbon double bond here. So I'm going to go ahead and just include that. We do have a double bond there, so we'll include that in our bit. We can go ahead and throw on all of our other explicit atoms. So we can throw on our oxygen with its H. We can throw on the nitrogen with its hydrogens. And we can throw on our bromine. And so now we're going to want to throw in our hydrogens, our hidden atoms, to make sure that all of our carbons have 4 bonds. So if we start at the bottom carbon there, we see that it has 1 bond to the carbon on the left, 1 bond to the carbon on the right, 1 bond down. So we're going to need 1 more hydrogen there. If we go to the left, clockwise, that one is missing 2. Same thing here. The next one is missing 1 hydrogen. Our next carbon has 4 bonds. We're good. The carbon below that also has 4 bonds, so that one's good. And so we just have this kind of sticking out carbon that's going to need 3 more hydrogens to make itself happy. Let's make that a little neater. Let's see if Kevin's counting is correct. Indeed, 9. Very good. All right. Any questions on that one? Okie dokie. I'm going to draw something that is going to kill me, but okay, let's see. Let's do the other way around. Okay. Alrighty. So, let's do the opposite. Let's convert this to the skeletal structure. So first thing we want to do is let's just see how many carbons we have in our chain here. We have, it looks like 6 carbons in our chain. So we might be tempted to say, okay, well, let's just do that. 1, 2, 3, 4, 5, 6. Ta-da, 6 carbons. But we have a problem here. And that problem, I'll go ahead and say it out. So we have a triple bond here, right in the middle of our molecule. This is something we don't do because the triple bond has 180-degree linear geometry. And so when we're drawing triple bonds, we can't have these kind of weird angles coming out of them. And so when we do have a triple bond in a molecule, we can go ahead and draw it. But everything coming out of that triple bond must be 180 degrees apart. So we have to keep the geometry there. So, one thing to note here, let's just say I'm going to put these two in blue. We have kind of our middle two carbons there. As drawn currently, I only have 4 carbons in my molecule overall, but this thing needs 6. And I know my triple bond is in the middle, so I need 2 on the left, 2 on the right. I currently have 1 on each side. So if I'm going to go ahead and do that, I can go ahead and add those 2 more in there. And now I'll have 6 bonds. Double bonds are cool to leave as this kind of weird angly thing, but triple bonds you're gonna need to make sure that you do have the 180 degrees there around it. So don't forget. For triple bonds, don't forget that. Okay, let's go ahead and put on all of our other stuff. So remember, in a skeletal structure, we do have to indicate all non-hydrogen atoms. So if we go left to right, that first chlorine there has, that first carbon there has 3 chlorines on it, so we're going to need to draw those in. Typically, we draw these as, we'll draw one kind of continuing the zigzag, and then we draw the other 2 on the opposite side of where that zigzag is going. And what I mean by that is we'll draw them like this very often. So we'll continue the zigzag with one of them, and then we'll put the other 2 on the top. What I mean by that is typically we don't do something like this. We don't do that sort of thing. Just to make it clear, if on a zigzag you're going to have substituents, that means other things, that are going to stick out either up or down, just to make it as clear as possible. So, I'm sorry, we don't need to do that on the last one, but that's typically how you'll draw your extra stuff. You'll draw it if the vertex is a little pointy up one, you put your other things up. If your vertex points down, you put your stuff down. All right, so just to make things clear. So this is just not really good. So don't do it that way. Try to keep things pointed nicely and evenly so it's nice and consistent. Okay, that aside, I'm going to hide that evidence. Let's see next. So that carbon's done. We've put our 3 chlorines on. Next carbon just has 2 hydrogens. So we're going to leave those off because we don't need to make our structure ugly. We have next our triple bonded ones that don't have anything on them. So we keep going. Next we have a bromine there. And so we'll want to put our bromine again because that carbon is pointing up, or it's the up part of the zigzag. We're going to put our bromine going up. We don't need to indicate the hydrogen on that, so just forget that. And then the last one, we have 2 oxygens, right? We have a double bonded one and a single bonded one. We could do that either way. We could do it this way. Or if we wanted, we could put the double bond where the OH is and put the OH down. It's typically more common that you'll see this vertical. You could totally, there's no problem with doing it the other way around. You could do this. That is okay. Totally okay to do it this way. We'll put our bromine up and our, oops, that's a chlorine. Either of these is okay, but typically you'll put your carbonyl is what that's called. typically that is the vertical one. So you'll either have the zigzag and then you'll have vertical stuff coming out. Typically a C double bond O is vertical. So again, I don't care. Either one will be okay. You'll see me, however, drawing it pretty much only the top way. So, but it's like totally okay to do it whichever way you want. So, all right. Any questions on that one? So note a couple things. So we learned a couple things here. Make sure triple bonds are linear. Keep substituents those are non-H things. We're going to keep those. How should I write this? So we want to keep them kind of on the same side of the zigzag, right? And just so we see that, if we were to just have some random zigzag, that means we want to keep our substituents on the same side. All right, so whatever we have that we need to throw in there, we'll keep those on the same side of the zigzag that your carbon is on. All right. Any questions on that last one? This one here. If we were to do a condensed formula for this, by the way, if that's the one where we look at the carbon, like one carbon at a time, we write them out, we could do that. It's probably easier to look at the Lewis structure to convert that, but we could go from either way. If we were to condense this structure, remember we will just kind of follow the carbons from left to right. So we would write this. I'm going to just copy this actually, and we'll go down so we have more room. If we want to condense the structure to write it out, we could do that. We would write CCl3, so we always start with carbon and write everything that's on it. So that first one is CCl3. Next we have CH2, carbon with 2 hydrogens. Then we have C, nothing else on it, right? There's no hydrogens, chlorines, whatever. We just have CC, carbon, carbon. We have CHBr. Typically you write hydrogens first. And then COOH. That's how we might write this as a condensed structure. But again, condensed structures are yucky. I don't like them. Not very common. So skeletal is always the easiest for all of us. So that's the one we'll be doing. So, but that's how you write that one as a condensed structure. Let's see, what else can I talk about condensed structures? Oh, yes. Sometimes if we were to have something like this, that indicates that it is a carbon double bond oxygen, as opposed to an oxygen that's bound with a hydrogen. And so what this will look like is we'll have our CH3CH2, and we'll have a C double bond O and then a hydrogen also on the carbon. That's to differentiate, just to make sure that we don't do something like this. Well, I mean, in this particular example, it wouldn't make sense to draw this particular one because now we have carbon with only 2 bonds. That means we're going to have problems. So, sometimes you'll see a parentheses in condensed structure like that to indicate that you have a carbonyl, a C double bond O. Typically, again, more common as we see kind of where it's more in the middle. This case is on the outside, but that's what that would mean. I'm probably not going to be asking you to convert things into condensed structures because I don't think it's all that useful of a skill. More often, I'll be asking you to convert either condensed or Lewis structure into skeletal. That's going to be more useful for us, or even going from skeletal to Lewis, just to make sure that we see our hydrogens there. So those are going to be the more important skills for looking at molecules like this. Alrighty, any questions on some of these? Do we want to do another one? I have an idea. Okay, let's do... Alrighty. Random molecule. This is the best because I can just come up with all these random molecules. It was such a pain in 111 to try and do Lewis structures because just having one central atom, it's so limiting. But with OChem, I can make, 20 carbon molecules for no reason. And we can just have fun with them. So, here's some questions. And number 4, what else can we say about this? How many? The only word you understand is carbon. That's great. Well, hopefully hydrogen's not bad, but how many pi bonds in the molecule? Okay. I mean, I don't know the answer off the top of my head either. We're going to have to work this through, right? Well, I mean, I can do 3 plus 2 plus 1 plus 5. Is that 11? Or how many did you say? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yeah, 14. Yeah, I forgot the methyl group there. So, very good. But let's go ahead and draw them out. So first things first, it's probably a good idea to see how many carbons there are too. So here's question 0. How many carbons? So if we want to do that, 6, 7, 8, 9, 10, 11, 12. So we have 12 carbons in this molecule. Yes. If we want to do hydrogens, I'm going to actually copy this thing first before we destroy it with hydrogens, because that's going to make it very hard to read. But here it is. And in fact, let me make it a little bigger. Let's go down. Oh, goodness. Okay. So if we want to put hydrogens on now, we're going to see all of these in the benzene part there. We'll just need one each, because those carbons all have 3 bonds, so that you're going to need a 4th one. That next carbon up there already has 4. This one is missing 1. This one's missing 3. The carbonyl is okay, it already has 4. The one with the halogens also has 4. The next one is going to need 2. And then our last one will be 3. So all together, if we count those up, the hardest part of this is counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yes. So indeed we have 14 hydrogens. So just so you know, I also will probably put up our first kind of homework assignment today, just so you can start taking a look at examples like this. It's not going to be due soon, because we're only, kind of barely starting this. So, but suffice it to say, there are your hydrogens. So I'll give you plenty of practice so you can start on your homework. All right, that's question 1. So we did that. We got 14. Question 2 is how many sp2 atoms? So we're looking at how many things have 1 pi bond. Aha. I think you fell for the same trap Kevin fell for last time. So if we look at anything that has a double bond on it, we're going to need to have anything that has a double bond on it will be sp2 in this molecule. We don't have anything that's sp, because all of these will just have 1 pi bond. So, let's use a different color. How about we use purple? So that's an sp2 carbon. That's an sp2 carbon as well. Both of those share that double bond. If we look at our next double bond, it's also going to have sp2 hybridization. Actually, let me do this one on the hydrogen one, because it'll be easier to see the number of bonds here. So this one will be all of these guys in the benzene are sp2. We can see that because they all have 1 pi bond each, and 3 sigma bonds. And then we also have these 2 atoms here. So don't forget to count the oxygen as part of your sp2. So generally, trying to think if there are any exceptions to this. If your sp2 atoms are only made from double bonded atoms, we'll say it's going to be an even number. So, right, because it takes 2 atoms to make a double bond. Why am I yellow all of a sudden? This is curious. Let's see, more light. Aha, now I'm normal again. Okay. What was I saying? Yes. So if it's double bond based, you're looking at an even number. So that's a kind of hint for you. So for sp2, generally you're going to have an even number. There's going to be one exception to that we'll talk about later on. But for now, even number because these are all from double bonds. Okay, so the answer there is we have 8 sp2 hybridized atoms. 7 of them are carbon, 1 is oxygen. How many lone pairs do we have in this molecule? Well, if we want to take a look at lone pairs, we know that carbons typically are not going to have lone pairs, so we're looking at heteroatoms. So we have 3 heteroatoms in this particular one. Because we have to indicate hydrogens on heteroatoms, we can see that none of these have hydrogens on them, which means that they're going to have lone pairs in order to fill their octets, right? So this fluorine, since it needs to have 8 electrons, it's got 2 from the bond to carbon, and so it's going to need 6 more electrons that are going to be in the form of lone pairs. All right. Same thing with the chlorine. And then our oxygen here is going to need 2 lone pairs because it has a double bond, so it's already got 4 electrons, just needs 4 more. And so as a result, if we were to count the lone pairs, we have 2 plus 3 plus 3, which is 8. So we have 8 lone pairs. What color did I do for that? Dark blue, okay. Or you could say 16 lone pair electrons, that's okay. So we have 16 lone pair electrons. Either way. But since I asked for pairs, let's stick with the top answer there. And then, what else did we say? How many pi bonds do we have? All right, so remember pi bonds are going to be double or triple. Anything that's a multiple bond there. What color have I not used? How about orange? Okay. If we want to look at our pi bonds, that's going to be anything that's not the single bond there. So we have 1 here, 2, 3, 4. We're going to have 4 pi bonds in this molecule. And so you see there's a ton of things I can ask you about these particular molecules that I can draw, just on kind of basics of figuring out their structures. Alrighty, any questions on that? So this weekend, it's definitely a good idea to practice taking a look at molecules like this. Just because, you know, they're written so simply, but we actually have a ton of information written within them, right? And so it's important that we can kind of talk about them. And so, Oz, where are you going, buddy? Notice it would be completely silly. Poor thing is like dying back there. Oh well. If we saw this, we have... What else do we have? 1 oxygen. If we were to try and draw the formula for this, how do we get 16 total? Oh, because each lone pair is 2 electrons, right? So, if I were to ask you how many lone pair electrons do we have, each pair is 2 electrons. Since we have 8 lone pairs altogether, 8 times 2 will give us 16. So it's just counting the electrons that are within those lone pairs. All right, hold up, I'm going to let him out. 1 second. All right, buddy, you want to go out there? Have fun. Okay. That makes sense? Cool, cool. Okay, yes. So if I were to give you this formula, this chemical formula, would you have been very easily able to get this molecule? Absolutely not. Right? A chemical formula like this tells us no information about the structure. And so, while that was, totally useful in Gen Chem, we could say, okay, yeah, we're talking about ethanol, we have C2H6O or whatever, right? But not useful for OChem. The reason for that is we can have, say, one formula. I mean, so this is not a condensed formula, Kevin. This is just a molecular formula, so just throwing the number of all the atoms and that's it. If you were to do a condensed formula for this, it would have to be... We would have to write... we would have to write that benzene part as kind of its own thing. We'd have to write... Oh, gosh. Just to indicate these are separate. C FCl CH2 CH3. That would be how we would draw this. Again, don't worry about this. It's a bit of an absurd thing to try and draw a structure or write a condensed formula like that for that particular structure. So I would not worry about that. That's kind of, it's garbage. It's very tough to indicate. And so in this case, we also have to use parentheses to indicate that those two carbon substituents are different from each other. Let's not get into that because it's really disgusting. This molecule here, given its chemical formula, could give us a multiple different structures. Out of this, we can get the following. These three structures that I've drawn here are all the same chemical formula, although I've not written them all out. Trust me on it, I suppose. So we're going to see that molecular formulas don't tell us anything about the structure. If we want, yes, we can say we have CH3, CHOH, CH3. We can do a condensed structure like that to tell us about the molecule, or we can say CH3, CH2, CH2OH, or CH3, CH2O, CH3. We can do that. These give us some information about the structure, but again, these condensed structures are not as kind of obvious to us as to how the atoms are arranged. So again, this is going to be kind of the preferred method for talking about molecules, and that is by structure. So we're no longer going to be talking about molecular formulas for anything that's organic, really. So, for something like water or hydrochloric acid, yeah, we can throw a formula on, no problem. But for anything that's carbon-based, we're going to need to draw the structures out. By the way, these are called constitutional isomers. We're going to learn many different types of isomers in this class, but this is our first one. Constitutional isomers have the same number and type of atoms, but different arrangements. So we can see in the first molecule, isopropyl alcohol, you don't need to know that yet, has the oxygen stuck onto the middle carbon. And it's a hydroxy. It has hydrogen on the oxygen as well. In the second one, just propanol, it has the oxygen on one of the terminal carbons there, so not in the middle. And we're going to see that those are going to have different properties from each other. And they'll be able to react. I mean, chemically they'll be pretty similar because they're both alcohols, but we'll go through that. And the last one is ethyl methyl ether. In fact, has the oxygen in between two carbons. And that's going to react very, very differently and have very different properties. Those first two would be liquid at room temperature. And the right one is a gas. Reason for that, hydrogen bonds, of course. No hydrogen bonds on the ether because it doesn't have any hydrogens. But we do have hydrogens on the oxygens in the other two. But we'll get to that. So those are constitutional isomers. They all have the same chemical formula, C3H8O. But we've arranged those atoms in different ways. Notice I could have done it this way also. The blue one there and the black one right below it, those are identical to each other. So I've just drawn them in reverse. But those are identical to each other there. So those two are the same. So we see here this particular formula can give us 3 different constitutional isomers. So we have the isopropyl alcohol, the propyl alcohol, and the ethyl methyl ether. Again, you don't need to know how to name those yet. But that was left to right. So we can see here we have very different molecules for each one. First two will be similar to each other, the other one very different. So, all right. I know what I need to do. So that's enough for today, chemistry-wise. Here's our homework. For those of you who have taken me before, which most of you have, you get to introduce yourself on Discord. Just like always, so many of you have, either you were in groups in 111 or you suffered through 113 and you survived, and that's going to be our homework for today. So for those of you who are not familiar with it, let's see if it's going to load here. No, I don't need lecture notes. So in the welcome channel again, which is where you'll go after clicking the Discord link on the syllabus or in Canvas, you're going to click the duck down there. So you just go ahead and click it. Ta-da! Now I've clicked it. Now it says 27, but I don't need to do that. You're going to go down to wherever we are. Oops. 221. There's my message. You all now get to write your just little intro. Just say hi, introduce yourself. Maybe just one little fact or something. Whatever it might be, if you're at Porterville or something, or if you're transferring, whatever, or something. So just put your little thing there. That's our participation for the week. For those of you who are watching this later on, make sure you do this hopefully by Sunday. It's my way that I have to take attendance, and I have to do that for the first 2 weeks. So just go ahead and introduce yourself. That's your homework. I will be putting up your actual homework, though that will not be due for a while. because we're only just kind of beginning here. All right, as always, if questions come up later, you are welcome to throw those at me on Discord. Just, I would practice this weekend as well. Let's see. Let me take out the book here. I'm sure there's plenty of problems in the back there. Yeah, so there's, if you take a look in the textbook, there's plenty of structures. I would, take some time, drawing those in multiple formats. Actually, I think chapter 2 is going to have better examples for that sort of thing. Oh yeah, there's tons. There's tons of these. So, tons of fun to talk about in here. So, just kind of look through those in the back there, and maybe just try practicing converting between them, just so you get as familiar with these structures as soon as possible, because that's going to just make things easier for you as you go through. And then I'm going to also put up a chart of functional groups. You're going to just want to get familiar with those. I'm going to kind of throw the chart up there, and I'm going to just very quickly explain what it means. So you're going to see something like this. It'll say ROH, or it might say even ROH like that. R typically is carbon or hydrogen, just some other anything really. If it has this kind of OH sticking off of a carbon like that, that's what's called an alcohol. We're going to see that the majority of reactivity is going to be limited to functional groups. Functional groups tend to behave similarly to each other. So alcohols tend to all behave the same way. So you're going to say things like that. That's what I want you to learn. I want you to learn kind of the general generic structure for a functional group and its name. I'm just going to put that out there. We'll continue talking about it next week. There's not really a deadline on it, but again, the faster you can do it, the better. Alrighty, so we're done for the day. I guess for the week, actually. So enjoy. Take the rest off. Start having fun with OChem. Hopefully the tears will not start quite yet, but we'll get there. All right. See you all next week.